Okay, good morning everybody. We'll make start now. Can I remind you of just a couple of things before we begin? By tomorrow night, you have to have booked all of your materials for your prac. Please go back and check. If you've already booked stuff and you think everything's organised, just please go back and check that it's actually what you booked, because I think in using the Google Docs document extensively, a few people may have accidentally deleted a whole column of information. I know that happened. And so I've rebuilt the Google Docs document. I think all the data that was there originally has been reinstated, but could you just go back and check? Now, particularly if you were one of the people that needed zinc nitrate, I think that zinc nitrate column disappeared at some point, and it's now back there. So just please go and check it. Yeah, so tomorrow night that will disappear. Tomorrow night at midnight that will go, and if you haven't booked your materials by then, that's it. Right, Timmy? That's it. So please do that. So Nahal, you've booked your materials. Send me your design immediately. We're going to continue with the alkenes today. Now, we haven't done this, have we? We haven't done this, have we? No. We did the alkenes, didn't we? Okay, good. And the reactivity is what we're looking at. So you should be able to name an alkene. You should be able to identify an alkene pretty easily from a structural formula. You should be able to work out that it's an alkene because it has the general formula CnH2n. It's an alkene, or from a structure, you should be able to tell that there's a double bond in the structure. If it's a condensed structural formula, CH3, CH, CH2, for example, you have to look for where that double bond is going to be, and it's there. And so whatever the case may be, anything that has a double bond is an alkene. So we're going to look at the properties, the reactivity of the alkenes. Now, the first and most important thing I want you to appreciate about the alkenes, which is very different to the alkanes, is that now these molecules have something in them that is quite different to every other part of the molecule. And that double bond, therefore, is the focal point of the molecule. This is a point where there is a very high electron density. So there are 4 electrons in that double bond, whereas everywhere else there are only 2. So if there is something that is searching for electrons, say something that's positively charged, or something that has a really high electronegativity that's searching for electrons, that double bond is where it's going to hit, okay? Nowhere else. That's the most likely site for the reaction, okay? So alkenes are pretty straightforward. We can predict pretty much what they're going to do and where they're going to do it, where there is the double bond. Okay, things that are searching for electrons, there's some new terminology, things that are searching for electrons that, you know, attack negative things, electrons, are called electrophiles. Electrophiles. So these electrophiles. So this is the name of a substance that searches for electrons, that is attracted to electrons. So this could be things that are electronegative. So chemicals that have very high electronegativity, or in fact it could be things that are positively charged. And they can attack that double bond. Now you'll see these terms quite often. Now we don't really talk about this type of reaction as an electrophilic addition reaction, but when you hear the word electrophile, you'll know that what this means is that this is a molecule or an ion or something that is attracted to negative charges. Now we will be talking about a different type quite a lot, not today, but I'll introduce the term now, nucleophile. So what do you think that is attracted to? Nucleus. And what charge does the nucleus have? Positive. So nucleophiles are chemicals that go in and attack positive charges. And so we will be looking at an example of a reaction called a nucleophilic substitution reaction a little bit later, which is just a substance, a nucleophile, that goes in, attacks something that's positive, and makes it swap around. So fundamentally quite straightforward, but once you get your head around the terminology and you understand what the terms mean, it's pretty easy really to work out what's going on. So you've heard this before: electrophile attracted to negative charges, nucleophile attracted to positive charges. An audiophile, for example, is a person that's attracted to high quality sound. You know, I am an audiophile. I am. I've spent a lot of money building my stereo system. I don't actually build it myself, I just buy it, but it's a really good stereo, and I love turning up the heavy metal music, the death metal music. Fantastic. I love it. I am an audiophile. Unfortunately, I can only do that when my wife is out of the house because she hates death metal, as most people do. So whenever she goes out of the house, and in particular when it's my turn to wash the floors, the whole neighbourhood knows, oh, Dan's washing the floors again, because the stereo's turned up and it's death metal. The whole neighbourhood's shaking. It's fantastic. I love it. But last lesson I got myself into trouble about talking about paedophiles. I'm not going to talk about paedophiles, but it's the same thing, you know, attracted to little people. All right? Anyway, we're going to be looking at electrophilic addition today, and we're going to be looking at how this double bond changes. So one of the things I'd like you to first of all overcome is a concern about why it is the double bond that reacts, because a lot of students think, well, a double bond is pretty strong. This is the least likely thing to break, right? Maybe some of you thought that, you know, the double bond, no way is that going to break because it's really, really strong. But the thing you have to understand, which you might not know just yet, but going on to a higher level you will, a double bond is not two single bonds. Definitely not two single bonds. Look, this is the bond enthalpy for a single bond, 348. You double 348 and you get 696. And 696 is not the bond enthalpy for a double bond. The bond enthalpy for a double bond is 612. So a double bond is not two lots of a single bond. A double bond is actually two different things. It's a normal single bond that looks like this. So it's carbon bonded to carbon, like a normal single bond where there are electrons directly between the two nuclei along what we call the internuclear axis, a line going through the two nuclei. That's a normal single bond. But then the other bond, the second bond of the double, is a really weird loopy kind of bond that goes above and below the internuclear axis. And there are two electrons there, and they can be there or there or there or there at any given point in time. So see, there's your normal single bond. This is the second of the double bond, and that second bond is above the internuclear axis, so the electrons are not held quite as firmly. They can be radiated with ultraviolet, infrared, you know, visible light. You can pull the electrons off fairly easily by attacking them with an electrophile. So it's actually one of the two bonds in a double bond is actually quite weak. So that's why it's the double bond that is actually the most reactive. Okay, we'll learn more about that in higher level. So alkenes, the double bond is where the party is at for these molecules. That's where all the action happens. Now, looking at some examples of reactions, they all react by what we call an addition reaction, because basically all you do to the molecule is you just add things to it. But to add something, the bond has to break. Normally it's between the two carbons, but if you just wanted to add something to the molecule, the bond has to break so that new things can be added. So you can see in this first reaction, ethene has a double bond there between the carbons, and it's reacting with bromine. Now, can you tell me why bromine will actually react quite well with this? What is it about bromine that makes it react quite easily with ethene? What do you think? Sarah? Speak up. I don't hear a word. Anna? What is it about bromine? What makes bromine so good at reacting here? What group is bromine in the periodic table? Do you remember? The halogen. What group is that? Group 7. And all group 7s have what property? High electronegativity. Yeah, so because bromine has a high electronegativity, it's going to be really good at attacking that thing that has lots of electrons. And eventually it'll coerce the electrons to form a bond with it. And this is what happened here. You see the bromine's just broken the double bond and ended up with 2 singles. So that's what we call an addition reaction. Nothing is taken away from the reaction. Nothing, there's no loss of anything. It's just 2 things being added together to make 1. And that's called an addition reaction. And this particular addition reaction, because it involves the addition of bromine, we call it bromination. If it involved the addition of chlorine, what would it be called? Chlorination. If it was the addition of fluorine, what would it be called? Fluorination. If it was the addition of iodine, what would it be called? Iodination. Yes, good. See, the terminology is really cool. It's really good. It's exciting. New words, long words, complicated, fantastic. Makes you sound really smart. Now, this particular reaction is important because it's actually specified in the syllabus as a separate syllabus point, 10.3.3, and it's used as a visual test for alkenes. Alkenes that all have a double bond, when you add bromine to them, do you remember the colour of bromine? Red-brown, very good. Red-brown. When you add bromine to it, or if it's really dilute, it won't be red-brown, it'll be yellow, something like that. But if you add bromine to an alkene, the colour disappears, so it becomes colourless. So this is a visual test, right? We can actually see a change in colour, and that only happens with alkenes. So if you had to identify an alkene, and this question is in the exams very often, substance X, when bromine is added to substance X, in the absence of a catalyst and in the dark, over a period of time the bromine changes colour and becomes colourless, then what functional group could substance X contain? You'd have to say double bond, because this is a visual test for that. All right? Another example of a reaction is the addition of hydrogen. Now, hydrogen is not as electronegative as bromine. Hydrogen is not as reactive as this, right? And that's why Ni is above this arrow. So it's a catalyst, because it needs a little bit of extra help. And nickel is a very common catalyst. We've seen it before. I think we've discussed it a few times. Nickel is a catalyst that you have to remember, but the rationale behind this is to remember that hydrogen is not very electronegative. Bromine is. No catalyst required here, because this is already pretty reactive. This is not. So we need a little bit of extra help, nickel. Okay? Hydrogen gets added, and we end up with ethane. Shinyu, what was your question?
If you're doing a visual test, couldn't the changing color
It could. Thankfully, triple bonds are not in the course, so the only one that is in the course is the reaction with alkenes. Yeah, so it's, because the syllabus is limited what you need to know, that's the only option. But definitely it can react in other ways. Because bromine, remember when we were looking at the alkanes, bromine, chlorine, all those things can react with alkanes, can't they? Do you remember? What was that type of reaction called? Substitution. Excellent. And what did you need for that reaction? UV. You see, that's why you have to remember the UV bit. Because if a question appears in the exam and they say, a chemical X reacts with bromine when exposed to UV light, then you know, well, now we're talking about free radical substitution of alkanes. But if they say substance X reacts with bromine in the dark, then you know it can't be an alkane, because the alkanes need that UV to get the reaction going. Okay? So, okay. All right. Hydrogenation is what this is called. Hydrogenation. Hydrogenation, bromination, hydrogenation, free radical substitution, exciting new electrophile, nucleophile, fantastic words. Hydrogenation is a really important process too. Historically, Napoleon was the first person, believe it or not, Napoleon was the first person to explore the potential of hydrogenation reactions. Napoleon, in his war efforts, in his war campaigns, the Napoleonic soldiers used butter a lot, and butter would eventually go rancid. And butter is a critical part of French cuisine. You know, they can't survive without their butter. So Napoleon supported research and the development of an alternative to butter. And he didn't know it at the time, but chemists found the solution through this reaction, a hydrogenation reaction. Very quickly, oils and fats are very similar in structure. Butter is a fat, and something like sunflower oil obviously is an oil. But the big difference is that oils are liquids, whereas fats and butter are solids. So the difference chemically is very simple. An oil, oils are basically triglycerides. There are 3 chains to an oil molecule. We'll get into this in a bit more detail later. But for now, 3 chains. Oils have carbon bonded to carbon, bonded to carbon, bonded to carbon, but then somewhere in the chain is a double bond. Okay? Now I'm going to draw that double bond downwards like that, and then the chain continues boop, 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 like that, and so on. And same here. Carbon bonded to carbon, bonded to carbon, bonded to carbon, bonded to carbon, and then I'm going to draw a double bond going upwards. And then the chain continues like that. And same thing here at the 3rd chain, carbon bonded to carbon, bonded to carbon, bonded to carbon, double bond, and I'll make this one just go straight. Wherever there's a double bond, you see how the chains become chaotic. The symmetry of the chains changes. The chain goes off in this direction, the chain goes off in that direction, and what was a molecule with 3 nice, neat little chains, at the point the double bond appears, the geometry changes, so then the chains go all over the place. So that's what an oil molecule looks like. But when molecules pack together to try to become a solid, you know, they get into an ordered lattice. Imagine this oil molecule that's got a big chain going up here and a big chain going down there, and then we get another one of these and pop it down underneath, and another one of these and pop it on top. Because of the chains going off in all these different directions, the molecules can't get very close together. And so the van der Waals forces between them can't really operate because the molecules are too far apart. And if the van der Waals forces can't operate and it's very weak, then that's why these things never form a lattice. They always become liquid. They can't actually solidify and stick together. Okay, so that's what an oil is. Fats, because they're solids, can stick together. So a fat molecule is a molecule that has 3 chains, but the carbon chains are, there are no double bonds. It's all just single bonds. And the carbon chains are really nicely ordered and very uniform. No double bond. Throw a double bond in, the thing goes crazy. Single bonds, it's nice and uniform, which means we can pack fat molecules fairly close together because there are no higgledy-piggledy chains that are keeping them apart. And so this can turn into a solid. So, margarines, they're in between. Margarines are in between. Margarines, we make margarines by getting oils polyunsaturated oils, so they're unsaturated because there are lots of double bonds, and we just pump hydrogen in it according to this reaction. And so if we wanted to just turn this oil into a solid, how many of these double bonds would we have to saturate? How many do you think? There's 3 here, 1, 2, 3. How many do you think would you be sure that you could turn it into a solid? 3. We just have to saturate them all. So if we put in lots of hydrogen and broke that double bond and broke that double bond and broke that double bond and saturated it, it would turn into that molecule, right? It would turn into a solid. But with margarine, they only slightly saturated. For each double bond, you need to add 1 hydrogen, right? 1 hydrogen molecule. So for each mole, you would have to add 1 mole of hydrogen molecules for each double bond. For this molecule, because there are 3 double bonds, 1 mole of hydrogen for each, you'd need 3 moles of hydrogen. So in a reaction, if you know you need 3 moles to turn it into that, then you'd only maybe provide 1 mole. So you might just break 1 of these double bonds. So let's break this one, for example. It would just be random. But let's break that one. We suddenly hydrogenate that, pump hydrogen in it, and then this chain becomes all nice and neat again. But then there's only 1 chain that's going off in an odd direction. But the molecule has straightened up a little bit. And if it straightens up a little bit, then we've got more chance to pack it together to turn it into a solid. So margarines are partially saturated. And that means that they're somewhere between being a liquid and somewhere between and a solid. So they're more a paste, which means you can pull them out of the fridge and they're still really spreadable. They're not solid and hard like butter. Okay? And it's just a chemical process. The partial hydrogenation of an oil creates a margarine. Okay, why have I told you this? It is actually, it has been a question in the exams in the past, you know, to describe an application of this reaction. And the obvious application is in the production of margarines. Yep. Oh, they can't. Oh, no, without putting nickel in the margarine. Oh, okay. No, the nickel can be removed from the reaction, and the nickel is basically just a surface upon which the reaction occurs. Like catalysts can be, the reaction can occur on that surface, and then you can just scrape it off or remove it, yeah, or dissolve it off or something like that. Yeah. But it would be interesting to test to see if any of the nickel does end up in the margarine. I suspect probably a little bit did, but I'm not really sure. That would be an interesting extended essay question, but too late. The extended essays are finished. All right. Next, addition of water. We can add lots of things to the double bonds. We can add lots of things. We can add, as you saw, bromine, hydrogen, water. When you add water, water's not particularly reactive. You know, you don't dissolve when you go in water. You don't explode when you go in water. You know, water's not particularly reactive. So water needs a little bit of extra help. Sulfuric acid there is the catalyst for this reaction. And you see what happens? The water molecule breaks. An H goes on one carbon, the OH goes on the other, and this is how we make ethanol. Now, there are 2 ways of making ethanol. Well, actually, lots of ways. But the most common 2 ways are fermentation, and that just makes ethanol. And then this is the industrial alcohol. So the stuff that we've got in our bottles in the chem bunker that's absolutely not drinkable alcohol is called industrial alcohol because it's made this way. And you can actually make any alcohol this way. So wherever the double bond is, you know, if there were 4 carbons and a double bond in the middle, then an OH would be added to one, the H would be added to the other, and you can make any alcohol you want from this type of reaction, called hydration. And then this last reaction is called hydrogen halogenation, because in this reaction, no catalyst required here, because we've got bromine, a fairly reactive element, highly electronegative, and so this reaction just Hydrogen goes to one, bromine goes to the other, and we make a bromoethane here. Okay, this is called hydrogen halogenation. So what do you have to know from these? You do need to know the names. You do need to know the conditions. You do need to be able to predict the outcomes. And in a moment, I'll write some example equations on the board. And do you remember me saying when we were talking about the health effects of things, and you have to make a comment about the health effects? Do you remember what I said that if you don't know? Respiratory illness, fantastic. Respiratory illness. If you don't know, just say respiratory illness or disorder or make something up. Respiratory syndromes or whatever. And you'll get your mark. The other thing, if you don't know what condition, because they will always ask you, what is the product, what is the name, and what conditions are required, then always say heat. If you don't know, just say heat. Heat is required, high temperatures, heat, and you'll get your mark. Because these organic chemistry reactions involve breaking really strong bonds, and they are therefore very, very slow, and so heat is always used to speed the reaction up. Sometimes you can predict what else might be needed. Let's just go back to this one, and you can perhaps tell me what other condition might be needed here. Well, obviously nickel catalyst. You just have to remember that. Heat. But what other condition? Think about what H is, what hydrogen is. It's a gas, good. So what other condition do you think you might need? Pressure, well done. Because this is a gas, hydrogen fills the whole room if we let it. And if we want to push it onto a molecule over there in the corner of the room, then we have to squish it onto that molecule and apply pressure to get it there. So high pressure helps to enable this reaction to proceed. So pretty much with any gases, you can say, yeah, high pressure also is required. Now, whether they actually use high pressure or not goes back to the equilibrium principles that we were talking about. Can you remember what they were? Some reactions would work really, really well under high pressure, but they don't use very high pressure because very expensive. Well done. Okay, but if you just said high pressure, that would be fine. Okay, and then the last type of reaction, you can even add alkenes to other alkenes, and here is ethene. And if we added ethene to ethene like this, then that double bond, when it's encouraged by a chemical called an initiator or promoter, and a chemical will come in here and grab an electron, which might break this bond, that might encourage that bond to shift over to replace it, or vice versa. One way or another, it is possible to rearrange the bonds, and this is what will happen. That double bond will break and form a link between those two carbons. And so we begin to get a chain, you see. Now this carbon on the right has 5 bonds. That's no good. 1, 2, 3, 4, 5. So that double bond, chain reaction, needs to shift over to the next ethene. And in turn, you end up with a massive ethene molecule. So that was the original ethene. That was the second one, the third one, the fourth, the fifth, the sixth, the seventh, the eighth. And it just goes on forever. Add more and more and more and more ethenes, and you end up with something called polyethene. And this is a polymer, plastics. All plastics are like this. Just a massive, massive molecule. Can be 800,000 carbons long in the case of polythene. It can be billions of carbons long with other polymers. Massive molecule. But because you're adding the same thing over and over and over again, what you find is the molecule has a really obvious repeating pattern. And it's pretty obvious here. This is the repeating pattern of polyethene. Polyethene, or abbreviated to polythene. A plastic. Plastics are really interesting things because it's not so much the chemical properties of the plastics, it's more the physical property. Because you've got such a massive molecule, the molecules, because they're so long, are really long fibres, they can get tangled with each other, and lots of fibres can get tangled, and then it produces a sheet of all these tangled fibres, which is a plastic sheet. Okay? And we can change the shapes of the fibres, or we can make them not just tangle randomly, we can put branches in to make them connect up, interlocking branches, so we can create design plastics for whatever purpose we want. where would the chain end? Well, that's a good question. You need something to start the reaction, and you need something to finish the reaction. And so just as you did with free radical substitution, you know, there's initiation, propagation, termination. You'd need an initiator molecule, and very often it's an ion, a positive ion of some sort, that would attach there. And then over here you'd need a terminator molecule that would also attach and stop the reaction. So to make the polymer whatever length you want, chemists have worked out that, you know, after 5 hours of cooking, we now need to put the terminator in, and that will make the molecule, on average, 800,000 carbons long. You know? The process is called addition polymerization. Why? Because the reaction is addition. You are just simply adding another molecule. The double bond is just simply shifting. So it's called addition. Addition polymerization. Now, polythene can be found in things like the shopping bags, can be found in the disposable gloves, can be found in things like witches' hats, can be found in stormtrooper helmets. And this is where I got myself into trouble with the other class, and I had to delete the recording because I said something I shouldn't have. It was inappropriate. And replicas of one of our executive leaders on staff. Unfortunately I named the person, but I just said, no, I won't say. I don't want to, no, I won't say. No. I'll leave it up to you as to who you think this might resemble. No, yeah, I got myself into trouble. I need to keep my mouth shut. All right. Yeah, so please, in your exam, you know, if they ask you a question, give an example of where polythene is used. Don't say replicas of our school leaders, okay? Say something like plastic bags. That's safe. All right. Now, you can make other polymers by taking, you know, just changing ethene to something else. Chlorine, maybe. So this is called chloroethene. As long as there's a double bond, that double bond can shift and it can create a polymer. So it can make this thing, but see here, here is the repeating pattern. The CCCl, 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 and so on. So that's a polymer, a repeating pattern, a polymer. And this particular polymer, we can summarize it. It's really stupid to write out, you know, lots and lots and lots of repeating things. So normally with a polymer, all we do is we bracket up the repeating unit, and the repeating unit here must be the original monomer, what's left of the original monomer. This thing here is called a monomer. It is not in the slides. Perhaps you'd like to add that. The monomer is the thing, the original molecule. So in this case, it's the chloroethene here on the left. And monomers join together by addition to produce the polymer, which is this thing on the right. And the polymer here, because it's made of chloroethene, which is also called vinyl chloride, the polymer is often called polyvinyl chloride or PVC. And PVC is this stuff, you know, the electrical conduits, stormwater tubing and drainage and stuff like that. That's PVC plastic. It's quite solid, quite rigid plastic, resists high temperatures pretty much. PVC tape and soccer balls, PVC, vinyl chloride. These are sort of common applications of vinyl chloride. And the last one, Teflon. Now, Teflon is a pretty common substance now, but revolutionary and still somewhat. The chemistry behind it is really, really interesting and easy to understand. So if this is the monomer, so it's tetrafluoroethene, 1, 2, 3, 4 fluoro, so tetrafluoro on ethene. Fluorine, highest electronegativity ever, right? There's not too many things that will take the electrons away from the carbon-fluorine bond. Pretty much nothing. Nothing's more electronegative than fluorine other than other fluorines, okay? And eventually, eventually things break down if you heat them enough, or even strong things break down, you know. But this pretty much will not do anything. So if we make a polymer of that, because it won't just won't react with anything, and make a long, long chain of it, and then stick that polymer onto a frying pan, for example, then you end up with non-stick frying pans, because the surface of the frying pan that has fluorine, 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 fluorine all on the surface, nothing can attach to it because nothing can form a bond with it because those electrons in there are held pretty firmly anyway. And, you know, so things just slip off. And fluorine has been used a lot. It's been used in fabric, in garments, to create a soft, slippery feel. It's used in non-stick frying pans, used on the nose cone of the space shuttle. It's used in paints. Fluorine's used in paints so that scribbles and so on don't stick. You can just wipe them off. Nothing sticks to it. So it's unusual, really, isn't it, that you would think that a substance in a laboratory that they discover that does nothing, you know, doesn't react with anything, boring, does nothing, you know, I'll throw it in the bin. But it is actually incredibly useful because the ability to do nothing is I shouldn't be giving you this message. The ability to do nothing is actually a very powerful skill, but not in your case. Okay, anyway, this is the repeating unit of Teflon. So you see, some people might say, the repeating unit, you don't have to write 2CF like that. Why 2? Because it's just C, 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 it's all the same. But the rule with a repeating unit is you have to show the original monomer. Okay? So if there were 2 in the original monomer, there must be 2 in the repeating unit. Okay? So you can't just write bracket. You can't just write this as the repeating unit, bracket CF2 to the end. No, that is a repeating unit. It is something that you can cut out and stamp to create the polymer, but by definition, the repeating unit must have the original monomer. Okay? Right, someone's nicked my speakers, and I wanted to show you a little movie look, the movie, these sort of visual things help you remember stuff. And I hope you remember this movie because the girl's a bit over-enthusiastic and a bit dorky, which is all right if you like dorky girls. And I do. But it's all about Teflon, so you can listen and then hopefully you'll be able to hear enough, but you can also play it to yourselves some other time, actually. All right, so watch.
For hundreds of great shows like this one, go to OnNetworks.com.
Hi, I'm Dr. Kiki Sanford. Today on Spin Science, we're going to switch through the science.
So all I want you to pick up from this is some applications of Teflon. Okay? course, you heard some applications of Teflon and some of the advantages, some of the disadvantages to it. What you would need to be able to do is, again, what you have to be able to do, according to the syllabus, is outline the economic importance of the reaction in alkenes. And so, in a question asking you about the economic importance of alkenes, the most likely thing for you to talk about is plasticity. We've just seen a video that shows, that discusses some of the applications of one particular type of polymer, Teflon. But imagine our life now, plastics, there are a lot of disadvantages. There are a lot of advantages. Improve the efficiency of motor vehicles, for example. Reduce the costs of lots of things. Make them more accessible to the wider community. So you have to sort of rave on a little bit about the application of plastic. A question like this would be worth 1 or 2 marks. That's all. But, 1 or 2 marks is easy enough. If you remember Dr. Kiki, it'll be okay. All right? Any questions about that? Our next slide is a look at the reactions to alcohol, so I'm not going to do that today. I'd like to finish off with just getting you to balance some equations, reactions that you've seen, examples of this reaction. So I'll throw up a few examples on the board, and then we can come out, balance them, and we can quickly discuss them before the end of the lesson. So with all of these, could you write out the name of the reaction, hydrogenation, conditions, and then balance it. Now, if I give you a whiteboard marker, if you've already had